Welcome. Today we have the fortunate aspect of being able to conduct a video recording of one of our lectures in the classroom setting here. Most of the videos that I've been conducting are from home, a little bit of limited environment. We're allowed to come on the campus here to pick up some supplies, and I'm taking advantage of that in order to at least provide you with a couple of lectures that are from the classroom. So it's amazing. I'm standing here in this $80 million state-of-the-art facility, which we just opened last August, with an advanced STEM center. The Student STEM Center here is amazing, as a lot of you have visited and utilized those facilities. And yet, there are no students in this building today at all. There's just a couple of faculty, such as myself, picking up supplies or recording lectures. And it's kind of sad. So we definitely live in a different world than when we started our semester. We had regular class meetings, we were doing labs in these classrooms, conducting lectures, taking exams, and there's the whole social interaction of student to student and student to professor. And that's just what I call the college experience. You, in a sense, are being robbed of a college experience. And we've seen society and the way it reacted to this coronavirus, the hoarding of toilet paper, hand sanitizers, canned goods, closures of social settings, bars, swap meets, beaches. We live in a different world. And some of the people have reacted very poorly to the situation, selling air masks, little dust caps that you can put over your nose on eBay. 3 of those for $145. Hey, that guy wasn't so bad. There was one guy selling 3 of them for $160. These are masks that cost a couple bucks a piece. And yet people are taking full advantage of the scare of the coronavirus and the infection that may follow if you don't protect yourself. The funny thing about those air masks is they don't work. They're basically dust prohibitors. They basically keep particulate PM10 dust particles from getting into your lungs and through your nose. So with that in mind, we've seen a breakdown of our society, the way people act. We've even seen our leadership, our congressional and senators, selling short on the market. They used inside information to conduct a trade. Anytime you use inside information and then conduct a stock transaction, that's called insider trading. People go to jail for that, as well they should. There are laws against that. But for some reason, our elected officials, our congressmen, and our senators were able to use inside information, sell their stocks before the market crash, and protect themselves. That's illegal, but not for Congress. I guess they're exempt. So with that in mind, given the interactions of people hoarding and all that's gone on, what and how would people react to a major earthquake in Los Angeles and Orange County? The probability of a major earthquake occurring in Orange County is very high. In fact, it's very likely that it will occur. It definitely will happen within our lifetimes. It may happen within the next 5 minutes, or it may happen in 5 years from now, or 50 years. Predictability of earthquakes to a precise time is problematic. We cannot do that. We know by looking at faults, we can look at the offset and how much offset has occurred over millions of years, and we can get an average earthquake offset, but we cannot put that down to a precise number. So here in the background, on the projector here, we have an earthquake. This earthquake actually occurred in Pakistan. As it turns out, earthquakes that occur in poor or developing countries see a higher death toll than earthquakes that occur in rich countries like the United States. And the primary reason for that is the type of construction, the building materials that they use in order to construct their buildings. In this case, this building here is made out of concrete. And concrete buildings are very rigid. They don't flex and they don't sway during an earthquake. And so these structures collapse, and due to the weight, anybody that's underneath this structure is killed. And so that's why countries like Pakistan, India, South American countries, Central American countries that are poor and developing have a higher death toll during earthquakes than rich countries. It's all because of the type of material. Here in the United States, our homes are mostly framed out of wood. Wood flexes, it sways. In fact, wood constructed homes are the best type of construction for during an earthquake. So earthquakes don't kill people. What kills people is buildings. So our goal is to construct buildings that will withstand earthquakes. Going back to the beginning of the semester, we talked about Alfred Wegener's hypothesis and how he hypothesized that if you took all the modern continents like South America and Africa, North America, and Europe, they would all slide together and fit like the pieces of a puzzle. And then 200 million years ago, this supercontinent Pangaea broke apart. Today, we realize that the Earth consists of tectonic plates, and these plates are always moving. So today, the South American plate is moving in a westerly direction, away from the African plate, which is moving east. And as these two plates move further and further apart, the Atlantic Ocean is growing. It is becoming larger. This whole process took about 200 million years. And it's along these plate boundaries where we find earthquakes. So especially South America, where the Nazca plate, which is moving to the east, is subducting, going underneath the South American plate. The South American plate, which is moving west, so these two plates are colliding, they're coming together. The fifth largest earthquake in recorded human history occurred in Santiago, Chile, or just south of it, in 2010. The largest earthquake in recorded history occurred in 1960 in the same area. That one actually were more centered in Santiago itself. So plate boundaries, these are areas where we have the largest earthquakes. And so we know that these boundaries, that these plates are in constant motion, that in the middle of the Atlantic Ocean, new crust is being added. And that convection is bringing hot magma. And as that hot magma intrudes, it basically pushes these plates apart. So every inch of crust we add in one part of the Earth, we had to subduct or get rid of another inch of crust somewhere else. And we do this along subduction zones. It's the subducted plate boundaries that pose the greatest threats to generating large magnitude earthquakes. This is particularly the case for South America, where the South American plate and the Nazca plates are converging, and the Nazca plate is subducting underneath South America. So it's these plate boundaries is where we see earthquakes. And as it turns out, there's two types of waves in an earthquake. There's a primary wave, which we call the P, and there's a secondary wave, which is also called S waves, or shear waves. These are the waves that cause the most amount of damage. Currently, scientists are working on, or seismologists, are trying to work on the differential time arrival of the primary wave and the secondary wave. As it turns out, the primary waves, they travel faster. And we can detect those waves, and then thereafter, following the primary wave is the secondary wave, which arrives a few seconds to a few minutes, depending on how far those waves traveled, or how far away the epicenter is. We're trying to use the differential time of arrival of these two waves to provide an early earthquake warning system. And so if there was a major earthquake that occurred, say, in the southern part of California, near the Mexican-United States border, in the Imperial Valley, there would be about a 30-second delay between the primary wave arriving in Orange County and the secondary wave. We can use that differential arrival time to provide a warning. So when sensors pick up the P wave, they can set an alert to your cell phone, which will give you 15 to 30 seconds to take action to prevent yourself from being vulnerable to the impacts of the earthquake. For example, if you're on a ladder, you can come down off the ladder. That's about the only really predicting model that has been in place right now, because when the earthquake occurs, we really don't know. So we're going to take advantage of this arrival times for the P waves and the S waves. So as it turns out, another thing that's difficult to predict about earthquakes is that faults move not at a constant rate. There's differential movement along geological faults, such as the San Andreas. In Central California, there's a small town called Hollister. They have little earthquakes there every day, little 1.0s, little 2.0s. And that is a part of the fault that moves constantly. We call that creep. So basically, this is very small earthquakes, and the pressure, the tension on the fault is released. It's the jerks that cause the greatest earthquakes. This is areas of the San Andreas Fault, for example, that have not moved in 300 years. So we have parts that are moving and parts that are not moving along the San Andreas Fault. And it's these areas where there is no movement that have high potential energy. There's a lot of stored energy, and that energy is then released instantaneously in a very large magnitude earthquake, and this is what generates the 7.0s, the 8.0s, the very large magnitude earthquakes. The Newport Inglewood Fault, which is right in our backyard, it goes right along the Pacific Coast Highway, right down Sunset Beach, between Warner and the pier, the Huntington Beach Pier. That fault travels right along, and in 1933, that fault moved. It generated a very large magnitude earthquake that destroyed Long Beach, and we'll talk about that later on. So we pick up these earthquakes on seismographs. So here are the first arriving waves, the primary waves. These aren't the waves that really cause a lot of damage. So we get the first primary wave, and then it's the secondary waves, the shear waves. These are the waves that cause the damage. They then are generated into a surface wave. This is what makes buildings swing back and forth. Things fall off shelves, canned goods slide off of shelves at grocery markets. And it's a differential of this P and this S wave. If an earthquake occurs and you have a seismograph right at the epicenter, the P and the S wave are together. But if you have a seismograph that's some distance from the earthquake, say 100 miles, there's going to be a gap between the arrival of the P and the S wave. And this is what we're trying to use right now, this differential arrival for earthquake warnings. And that warning is going to be literally 15 to 30 seconds. Earthquakes occur without notice. This is a double-decker bridge in the San Francisco Bay Area. This bridge collapsed during the 1989 Loma Prieta quake. And so when earthquakes occur, they send a shock wave, and that shock wave travels throughout the earth. So the amazing thing is, if you have a good seismograph, and an earthquake occurs in China, we can pick up that earthquake in the United States, in North America. We would not be able to feel that earthquake. We could not detect that earthquake at all as human beings, but sensitive seismic equipment that has rods that extend to the ground can actually pick up these seismic events. So seismographs measure earthquakes from around the world. And as an earthquake occurs, it generates a shock wave. This is a release of energy, and that energy then transmits across the surface of the earth. So obviously, the closer you are to the epicenter, the focus where that earthquake occurred, the greater amount of movement you're going to feel, the greater amount of shaking you're going to feel. The further you're away from that event, from that seismic event, the less energy you'll feel. So we measure earthquakes on a scale called the Richter scale. And as it's graduated, it goes from 0 to 10. And look at the numbers here. So let's look at the 1.0 earthquake. 20 million units of energy are released in a 1.0 earthquake. Now, move to a 2.0, where 630 units of energy are released. So the way the scale works is that a 2.0 earthquake is 30 times more stronger than a 1.0. So by the time you start to experience seismic events around a 7.0 is 30 more times larger than the 6.0. The 6.0 was 30 times more larger than the 5.0. The 5.0 was 30 more times more larger than the 4. And so you can see what happens with these numbers here is that they go up to the trillions and the billions, and this is how we measure earthquakes on a scale called the Richter scale. So the largest recorded earthquake in human history occurred in 1960, San Diego, Chile earthquake. It was a 9.4, and that is the largest known earthquake in human history, although there have probably been larger earthquakes prior to humans recording such seismic events. So earthquakes, it's a sudden movement in the Earth's crust. This is a release of energy. So as these tectonic plates move, that energy is transmitted in the form of a wave similar to a sound wave, or to a wave that would occur if you threw a rock into a lake or a pond. You get that rippling effect. That is basically what earthquakes are. We have an event that occurs called soil liquefaction, and this is pretty dangerous in coastal areas. If you have sediment that is super saturated with water, that water comes to the surface and is under extreme pressure, and that water can actually break apart concrete, asphalt, and roads. Fails during liquefaction. That occurred during the Loma Prieta quake in the San Francisco Bay Area in 1989. And then earthquakes that occur in ocean plates, around where two ocean plates come together, such as out in the Indian Oceans, they produce tsunamis. And tsunamis basically are a seismic wave that travels in water, and when it approaches shallow water near coastal areas, that energy is transmitted into a huge wave that people often refer to as tidal waves. We'll talk about tsunamis and liquefaction later on in detail. So here, this is actually a double-decker bridge that actually collapsed in Kobe, Japan. The Japanese are the leaders when it comes to earthquake prediction and for earthquake building, for building buildings that are more tolerant to earthquakes. And the primary reason for that is that they've had a higher amount of earthquakes. They've had a very large number of earthquakes occur in Japan. So when a fault moves, there's actually two terms that the media likes to mix up sometimes. So the focus, this is where the fault actually moved. This generates the energy. The energy then radiates out, and as that energy radiates out and makes contact with the surface, this is what we call the epicenter. So the epicenter is where the energy of that earthquake makes contact with the surface. Now if you have a focus that's deep within the crust, and so this fault moves at a depth, that's better. Because what occurs is that the shock wave, the energy, is absorbed. It's dissipated out by the rock. If the focus and the epicenter are the same, and they can be, and that would occur if this fault moved right here to the surface, then that shock wave is basically radiates out across the surface, and those result in very high magnitude earthquakes. A few years ago, Seattle-Tacoma area experienced an 8.0 earthquake, but that earthquake was so deep that by the time the shock wave made it to the surface, it was a very mild seismic event on the surface. So deep-seated earthquakes are the best. When the focus and the epicenter are one and the same, that's when you have a high degree of damage, because the waves, the energy is transmitted across the surface of the earth where we live. So this is what happens to land, and this kind of freaks people out. Rock, dirt, something we see as solid, actually acts like water. It actually has a rippling effect. Last summer we had an earthquake in Huntington Beach. Actually, the epicenter wasn't here. It was actually at Ridgecrest. I was actually watching the Huntington Beach parade, sitting there at the curb on a skateboard, and I literally could see the rippling coming across the asphalt. And I was telling people around me that this was an earthquake that had just occurred. It occurred to the north and to the east of us, because I could tell by the way the waves went through the asphalt. And we later found out that the epicenter was in Ridgecrest, which is north and east of us. Actually, the state of Nevada, Las Vegas, Nevada, was actually closer to the epicenter than we were, but we did feel it as well as people in Nevada felt that quake. So the ground can actually act like water, and it will transmit this shock wave. And what that does to power poles, buildings, is it compresses them and it stretches them. So it extends them outwards, it then pushes inwards and compresses them, and then relates in tension outward. So you get this rippling effect, almost like a slinky, the spring-loaded slinkies. And the result is damage. So we're going to go now and look at kind of a chronological history of earthquakes in California. We're going to focus on the major quakes and focus on Southern California, although we are going to talk about one Central California earthquake, the Loma Prieta quake, was really important. But the first major earthquake that occurred in California in historic times was the 1906 San Francisco earthquake. So San Francisco had basically two tragedies at that time. They had the earthquake itself, which took out a lot of buildings, and then they had a fire. The fire resulted from kerosene lamps tipping over during the earthquake event, setting wood structure fires on fire, and the city burned for 3 days. The largest earthquake kind of in recorded history occurred in 1857. It was called the Fort Tejon quake. It occurred basically out between Palmdale, California, and a town called Ridgecrest. That earthquake, if that had occurred today, that would just have devastating consequences to Los Angeles, because this is a part of the San Andreas Fault that's just north and east of downtown LA. And so LA is vulnerable because of the San Andreas Fault and another recently discovered fault called the Pointy Hills Blind Thrust Fault. So we'll talk about those. So the first kind of recorded earthquake in California that actually got scientists working on an earthquake and understanding what earthquakes were was the 1906 San Francisco quake. The city was destroyed by the earthquake itself, and a fire followed, which burned for 3 days. The San Andreas Fault moved between 6 and 8 feet over a period of about 15 to 30 seconds. It generated a 7.8 Richter scale quake. And this is actually a fence. So the San Andreas Fault goes right across this fence here. This is a fence that separated out 2 farmyards or pasture lands. This fence was once connected. This fence basically pulled apart. The San Andreas Fault is right through here. And this shows the offset that occurred. These buildings in the background here were constructed out of wood, so they survived pretty good. So wood constructed homes are the best construction during an earthquake. This is a statue at Stanford University that headbutted the concrete. The reason that San Francisco burned for 3 days was simply that the houses were built so close to one another, and they're made out of wood, so when one house caught on fire, it just was a domino effect. Each house next to it just burned up, and basically the city burned for 3 days. So here's actually a picture of that 1906 fire. And in fact, back in 1906, they didn't have the internet. They didn't have modern news broadcasting. They basically had newspapers and telegraphs. And eastern cities such as New York, Pennsylvania, Philadelphia, Chicago, those newspapers reported that San Francisco was destroyed by a fire. And it was. But the fire was caused from an earthquake. So the irony here is that because San Francisco burned, legislators and city officials passed laws requiring public buildings to use brick, because brick doesn't burn. So here are the streets of San Francisco. This is why infrastructure, streets, are very vulnerable to quakes, because debris litters the streets. And today, with our modern society, underneath our streets we have buried gas lines, we have buried water lines. Those water lines can rupture and wash out the street. Gas lines rupture and catch on fire. We saw that in the Northridge quake. City Hall destroyed. So the people who we depend on for assistance, even City Hall was destroyed in that 1906 San Francisco quake. The next significant seismic event to hit California, and this is probably the most important earthquake with regard to legislation and building codes, was the 1933 Long Beach quake. The 1933 Long Beach quake occurred along the Newport-Inglewood Fault. The epicenter was right near the Newport Beach, Huntington Beach political boundary, right where the Santa Ana River discharges into the ocean. It was actually in Newport Beach, offshore, right on 64th Street. That earthquake resulted in the deaths of 115 people, and it destroyed every school in the Long Beach area. So this is one of the buildings. These buildings used red brick as their construction. Now remember, the 1906 San Francisco quake, the fires that followed the earthquake were the result of wood homes built close to one another, and when one wood home caught on fire, it spread to the next and the next. So then city planners came up with the idea, we'll use red brick. Red brick doesn't burn. But the problem with red brick is that the mortar that holds the brick together almost acts like water during an earthquake. It almost becomes liquid, and these bricks are able to slide and move independently of one another, resulting in a total collapse of the structure. This is actually one of the schools. So Long Beach, all of its major schools, its elementary schools, its middle schools, its senior schools, its high schools, were all destroyed during this seismic event. All those buildings had one thing in common. They were all made out of, or constructed from, red brick. And the reason behind that was to prevent fires. Wooden structures do pretty well in earthquakes. You can see the cracks in the asphalt in the street. So the Long Beach quake, 1933, a magnitude 6.4. The Newport Inglewood Fault moved, and the epicenter was at 64th Street, right in Newport Beach. It was actually offshore. This is where the Newport Inglewood Fault goes offshore. And this is just south of Huntington Beach. So the top picture there shows Franklin School, built out of red brick. It had a basement and then 2 floors. The entire structure was made out of red brick. During an earthquake, that structure completely failed. And so when they rebuilt it, they built it out of materials other than red brick. And in fact, because of this earthquake, there were 2 pieces of legislation that were passed. One was called the Field Act. And the Field Act basically outlawed the use of red brick in any school building. So they could no longer build schools out of red bricks, and then rebuilt Franklin Middle School. They could not use the red brick because it's very vulnerable to earthquakes. So this basically shows a map of the Long Beach area. This is the Newport Inglewood Fault. It actually starts in Hollywood. It transverses through Long Beach. It then goes along the coast, right down the Pacific Coast Highway through Long Beach, or through Seal Beach, into Sunset Beach, and then through Huntington Beach. It goes offshore right about where the pier is. In fact, the pier was built, the Huntington Beach Pier was built where it is, because that's a point break. And that point break was formed because this is where the Newport Inglewood Fault goes offshore, and it travels offshore for a while, and it becomes landlocked again near San Diego, and that part of the fault they call the Rose Canyon Fault. So buildings throughout the Carson, through Torrance, Long Beach, Compton, even Seal Beach were damaged. A lot of businesses, buildings collapses, and schools. So these are actually the schools that collapsed during that seismic event. Franklin Junior High School, John Muir Elementary School, Willie Elementary School, Jefferson High School, Lowell Elementary, Long Beach Polytech, that's still there, Burbank Elementary, and Roosevelt. So this earthquake occurred in the afternoon, after school had gotten out. If this earthquake had occurred during school hours, the death toll would have been much higher than 115. And a lot of those deaths would have been school children that would have been trapped in structures, in school buildings that would have collapsed. So the Field Act, the second act followed, called the Riley Act, that was also passed in 1933, and that basically outlawed any red brick construction in any public building at all. Even public buildings like shopping centers, movie theaters. Even though they're privately owned, they're open to the public. You could not use red brick in any of those, the construction of any type of venue like that. So here shows some of the red brick that fell onto a car here outside of looks like a little drugstore. People are homeless. They're living out of tents. It's like a 3-story building that collapsed during that earthquake. This is such a neat picture of Long Beach because look in the background here. All these oil derricks out here. Oil derricks all over the place. Kind of looks like Huntington Beach. Huntington Beach, actually, when this earthquake occurred, Huntington Beach wasn't the city it is today. It was mostly a town of oil derricks. This is actually a hotel called the Huntington Hotel in Long Beach that collapsed. Here's the sidewalks. So a lot of people were killed as they exited buildings. The red brick facade, the exterior of the buildings collapsed, burying these people under the debris. And they had more people who were killed as they exited buildings. Let's now look at the Northridge quake. So Northridge occurred in 1994. It's probably the most recent earthquake that occurred in Southern California. 6.7 on Richter scale. When this earthquake first occurred, some scientists thought it was the San Andreas Fault that had moved, but latter studies revealed that it wasn't the San Andreas Fault that had moved, it was actually a blind thrust fault. And now research within the past few years, out of a couple of professors from San Diego State University, are now hinting that the Northridge quake was a blind thrust fault, but it was actually a newly discovered thrust fault called the Pointy Hills thrust fault, which is a rather large thrust fault that extends across the Long Beach area into Los Angeles County. So LA County has this huge buried thrust fault called the Pointy Hills thrust fault. And they think that this fault might make Los Angeles more vulnerable to an earthquake than the San Andreas Fault. So San Andreas Fault has the probability of creating an earthquake that could impact Los Angeles, and then the Pointy Hills thrust fault. So the Pointy Hills thrust fault starts actually in the Pointy Hills, which is right near the 57 freeway near Diamond Bar, and extends and goes kind of north and east and abuts against the mountain ranges, the San Gabriel Mountains. And this fault is actually kind of pushing against the San Gabriel Mountains. So this is actually a map showing the Pointy Hills thrust fault. So this is the area of Orange County where the 57 freeway goes up and then goes into LA County. And this fault kind of travels across the LA basin. And this fault is actually kind of pushing towards the mountains and basically causing those mountains to uplift. It's basically pushing itself against the Santa Monica Mountains. And a lot of stored energy in this fault. The good news about this fault, it only moves about once every 500 years, but when it does move, it moves with a vengeance, creating 8.0 magnitude earthquakes. And so that's the good news and the bad news of that fault. So the Pointy Hills fault, it travels in a different direction than the most fault. So this actually would be our Newport-Inglewood fault here. So here's the Newport-Inglewood fault, which actually extends to Hollywood, goes along the coast here. And so you see that most of these faults are kind of going from the north to the south. Pointy Hills kind of does a little bit different direction. It travels almost west to east. Not quite the same direction of movement. And they think that the Pointy Hills thrust fault is actually a stress reliever for faults like the Newport-Inglewood, the Whittier Fault, and the San Andreas Fault. So right now, the area of Pasadena and the San Gabriel Mountains are the fastest, or the second fastest, uplifting mountains in the world today. The number one fastest uplifting mountain in the world today is the Himalayan mountains, where India is slamming into China. So mountains in our own backyard are second, which is not really good news for Los Angeles area. What are the things we learned? So every time there's an earthquake, we learn something. And the primary learning tool that came out of the Northridge quake was that freeway pillars collapsed. So that resulted in legislation that required Caltrans to go and refit all the pillars. And The remediation for that was simply to take very thick steel cable, wrap those pillars with that cable, and then encase them in steel. So the hope, the theory behind it, is that if the pillars stay in place and we can keep them from failing, then that will keep the bridges, the flybys, the overpasses. And so that is the one thing that came out of the Northridge quake, was that freeways failed. And they failed in areas where you have a lot of overpasses, bridges, flybys, and the collapse of those freeways was primarily due to the pillars collapsing. And so here's a shot of some of those pillars that collapsed. And so as you're driving down a freeway during an earthquake, you would be able to feel the earthquake because the rubber tires, the shocks, the suspension on your car basically absorb the shock wave. And so it's pretty hard to really understand what's going on until you start seeing segments of road collapse before you. Let's now jump to 1989. Loma Prieta earthquake occurred in the Bay Area, but the epicenter was 40 miles to the south. Where the earthquake occurred, there wasn't as much damage as 40 miles to the north of where the earthquake occurred. And the primary reason for that is the type of geology, the type of rock that exists. So this is very important. So what we learned in the 1989 Loma Prieta earthquake is that more damage occurred in the Marina District of San Francisco. This is a classic case for stable versus non-stable material. So the best material to build any building on, a house, a tall building, is granite. So granitic rocks have a tendency to absorb the shock wave of an earthquake. Sedimentary rocks that are soft tend to move, making foundations on buildings vulnerable to collapse. And if those soft sedimentary rocks are saturated with water, that water can come up under hydraulic pressure and actually cause buildings to fail. And so wood constructed homes are the best. These buildings are very flexible, and concrete buildings and brick buildings are the worst because there's no flexibility in those buildings whatsoever. So this is actually the double-decker bridge in Oakland. This bridge collapsed. They did not rebuild it. This is very similar to a bridge that they had in Kobe, Japan, that collapsed a few years before. So this type of construction, we can definitely see, is not very viable for earthquake-prone regions. And so the type of material of where you build on is really important. And a lot of the Bay Area has landfills. So what we have done as humans is we've taken rock and gravel and we push it out into the bay to create more land. I have some neat pictures that show the San Francisco airport is built like this. It actually built out in the bay, and they actually took sand, gravel, rock, and they filled in part of the bay, creating the runway. And what's bad about that type of construction is that these sediments then fill up with water, and then that water comes up during a seismic event, during an earthquake. That water is under pressure, and it literally pushes the asphalt, the concrete aside. So this is kind of a picture showing this. So here we have 3 layers. We have the water-saturated sediments. Overlying that are the sedimentary rocks, and then there's pavement. During an earthquake, as a seismic event occurs, as waves travel through this, these seismic waves take this water and they push it upward under great pressure, and this water then breaks through the asphalt or the concrete. And if you have a building that has a concrete foundation and that concrete foundation is perched or it's compromised, then the building is going to collapse. And this is basically what liquefaction is. So this is actually a map showing the Bay Area. So this is Oakland, this is the Bay, and this smaller map here shows the big picture. Here's Oakland, and this is the epicenter of the 1989 Loma Prieta quake. 40 miles south of Oakland, but yet Oakland sustained more damage because of the type of rock. So as that seismic event occurred near Santa Cruz, that shockwave traveled north. And as that shockwave traveled across the Bay Area, it traveled through 3 different types of rock. So this kind of peach colored material here, this is bedrock. This would be granite. The yellow material out here is soft sedimentary rock that's kind of naturally occurring. And then this is partially filled, that humans have filled in the bay to create more land, and natural rock that's just super saturated with water. And so as that shock wave travels through these three different types of geological settings, it produced a different type or size of seismic event. So this is the seismograph showing the wave frequency for bedrock. So this is the size of the waves that are generated in the bedrock. So you can see that this is pretty small event in bedrock. As that shock wave now travels through the sand and gravel, this yellow area here, you can see that, notice the difference between this seismic wave and that seismic wave. A lot more shear, a lot more rolling, very damaging to foundations of buildings. And then in the areas that are super saturated with water, this is the soft sediment that's saturated with water. This is where you get the liquefaction, and look at the shock wave that occurs here. So if you compare these three shock waves, the bedrock, sand and gravel, and the soft mud, this is why the open area sustained far more damage than the focal point where the earthquake actually occurred near Santa Cruz. In fact, town of Santa Cruz had damage, but their damage wasn't anything like what they had up in the Bay Area. And so this was an important lesson, and this is brought to question, should we really use the Richter scale to determine the size of an earthquake? Because if you're living here, and just a few miles away, you're living out here, you're going to experience a completely different seismic event than these people over here. And this is in an area that's pretty short distance. So now what seismologists are looking at is possibly doing extensive mapping and then rate areas based on the geological setting, the type of rock, and those areas are going to be rated for vulnerability and earthquake predictions. This is actually good for insurance companies, so they can actually take some risk assessments and figure out, how much they're going to charge to insure an earthquake or insurance policy for a house here versus one that is here. So this is actually a building. This is a 3-story apartment complex that was constructed on very soft sedimentary material that was super saturated. The first floor of this apartment complex collapsed, and this building basically literally started to pancake one floor on top of another. And this is actually in the Bay Area. So buildings that were right near the epicenter, near Santa Cruz, didn't see nowhere near this type of damage. So the damage of this building was primarily because of the type of geology, the rocks this is built on. So this basically shows a map view of where that earthquake occurred near the town of Santa Cruz. That then seismic event generated a shock wave that radiated out. As that shock wave traveled north into the Bay Area, this is basically just a big earthquake on all the little yellow ones or clusters. The different type of geology saw a different seismic event. So if you were built on bedrock, very small seismic event. If you're built on soft mud or sand and gravel, you had a much larger seismic event. And if you were on the sedimentary fill or the soft material that was saturated with water, the seismic event that you would experience would have been a much larger magnitude event. And this is all within the same geographical area. So let's look at now at San Andreas Fault. San Andreas Fault is a plate boundary between the Pacific Plate and the North American Plate. So basically what's occurring in California is anything that is on the west side of the San Andreas Fault, that part of California is moving to the north and the west. Anything that's on the east side of that fault is on the North American Plate, and it's moving to the west. So the San Andreas Fault is a transform fault, also known as a strike slip, but we use the word transform for the San Andreas Fault because it's a plate boundary between two plates that are sliding past one another. I love this map here. This map tells you the probability of an earthquake. So let's say you knew nothing about earthquakes, or knew nothing about California. You just knew, let's say you're from New York. Your name's Vinny, and you're from New York. And you think I'm moving to California. And what you know about California is, yeah, Hollywood, beaches, surfing, and earthquakes. And if you showed Vinny this map and say, hey, look, the town of Parkfield has a 90% probability of an earthquake. But over here, in the Crisol Plain, there's only a 10% chance of an earthquake. Vinny would probably want to move to the Crisol Plain. But yet, he would be better off moving to Parkfield. So you say, why Parkfield? So Parkfield has a 90% chance of an earthquake. And that's actually good. And the reason it's good is because Parkfield has very small magnitude earthquakes, 1.0, 2.0s. So this part of the San Andreas Fault moves on a regular basis. It's relieving that stress. It's relieving that tension, that shear force that's built up in the fault is being relieved. Where in areas such as the San Bernardino Mountains and in the Crisol Plain, these parts of the San Andreas Fault haven't moved in hundreds of years. In the case of the San Bernardino Mountain area, the area between Coachella and Cajon Pass, that segment of the San Andreas Fault has not moved in 300 years. So what's going on with our San Andreas Fault is we have some segments that are moving continuously, day by day. And we have some areas, such as in the Crisol Plain, San Bernardino, and up here in the San Francisco Peninsula, that haven't moved in hundreds of years. These segments of the fault are building tension. And that tension, we fear, will be released in one catastrophic quake, 8.0 or higher. And what's bad about the San Bernardino Mountain segment of the San Andreas Fault is that it lies between two great big gigantic blocks of granite. The San Jacinto Mountains to the west and the San Bernardino Mountains to the east. And all that energy, when that fault moves, is going to act like a funnel. It's going to take that energy and push it right towards LA Basin. And so Los Angeles is very vulnerable to this southern segment of the San Andreas Fault moving. It also has vulnerability due to the Crisol Plain, which is just north and east of Los Angeles. This is another segment of the San Andreas Fault that's locked and loaded. Lots of energy, lots of potential energy built up there. And then, of course, out in LA Basin, we have the Pointy Hills Thrust Fault now. So LA basically has three areas of vulnerability from earthquakes: San Bernardino, Crisol, and the Pointy Hills Thrust Fault. So all three of those have a large probability of generating a very large magnitude quake. So this is actually at Cajon Pass. I took this photograph. So this is Interstate 15. Victorville will be behind me. As you go down the hill, you go into San Bernardino. So on this side of the highway, this is the Pacific Plate. This is where we live. So anybody in Orange County, most of LA, all of LA County, San Diego counties, eastern Riverside, and eastern San Bernardino counties are basically on the Pacific Plate. The rest of California and the rest of the United States, Nevada, all the way to Florida, basically are on the North America Plate. So what's occurring in this area is that this plate is moving to the north, this plate is moving to the west. And hence, this is a transform plate boundary. And this is also part of the San Andreas Fault that has not moved for 300 years between here and going down into Coachella near the Imperial Valley. We have built many freeway interchanges right across branches of the San Andreas Fault. It's amazing. Right out where the 60, the 10 freeways come together into 15, right across the branch of the San Andreas Fault. This is actually an aerial photograph of the San Andreas Fault out in the desert. So here we see a dry wash, flows down, hits the San Andreas Fault, and this offset here. So you can see this offset that these two segments of this wash were once connected, but they've been offset because this side is moving in this direction relative to this. So this is what we call a transform or strike slip fault. This is really a neat land use, if you time it just right, earthquakes should actually be beneficial. These are orange trees. And see how these orange trees are a nice little straight line? And boom, they all of a sudden offset here. So the little red dotted line I put in here, this is the San Andreas Fault. This is near a little town called Hollister, California. Hollister has earthquakes every day. And it's an area of the San Andreas Fault that we call a creep. This is where the San Andreas Fault moves all the time. Now imagine, if your oranges are ready to pick, rather than hiring fruit pickers, get an earthquake, shake all the oranges off the trees, and you just go down and pick them up. This is a Landslides photograph. I took this off a satellite image from NASA's webpage. I enhanced the photograph by using the infrared spectrum. So infrared takes everything that's green and turns it red. This is the San Andreas Fault right here. This elongated black thing right here is a reservoir. So under infrared photography, blue shows us as black, green shows us as red. And the reason I like the IR band is because it really enhances the urban aspects. Look at this. This is the San Francisco runway for the San Francisco International Airport. Is that a natural landform? No way. This is where we have taken sand, gravel, and rock from the mountains, transported, and dumped it out here, and created a runway. This runway is very vulnerable to an earthquake because the sediment is going to be saturated with so much water. So all this blacks up there is the water. This is the bay. And a lot of areas here, we see these little square areas. These are where we are creating land for docks and for shipping and moving goods and services in and out of the San Francisco Bay Area. So this next photograph here is of this reservoir right here. And this right here is a dam. This is right on the San Andreas Fault. So here is a picture that I took out of a commercial airliner. And the dot right here, the dotted line here, is the San Andreas Fault. This reservoir, this dam, built right across the San Andreas Fault, which holds back all this water. So this is the same structure that's in the previous picture here. Here is the dam, the San Andreas Fault. This is the interstate. And I bet you if you conducted a survey, if you went to these homes and knocked on people's doors and asked them, do you know you live right across the freeway from the San Andreas Fault? They probably weren't aware of it at all. They're actually building new homes and selling new homes right at the foothills of the San Bernardino Mountains. I mean, a stone throw away from the San Andreas Fault. And I'd be willing to bet that the people who purchase those homes have no idea they're living on a segment of the San Andreas Fault that hasn't moved in 300 years. That could generate a shock wave or magnitude earthquake of an 8.0 or greater. That's part of our society. So the San Andreas Fault goes right across the San Francisco Bay Bridge. It will collapse someday. And this is what's strange about earthquakes. So here we have this building here, sustains very little damage. Right next to it, this whole building collapses. And this is why predictability of earthquake. And remember, it's not the earthquakes that kill people, it's the buildings that kill people. So if you were in this building during an earthquake, chances are you would have been unskilled, not injured. Over here, probably killed, burial planned, you're buried in the building. And so as it turns out, what we're doing in California is we're trying to get an assessment of what areas of California are more vulnerable to earthquakes and what areas are less vulnerable. So anything that's red, this would be the very high-risk areas. Notice right along the San Andreas Fault right here, very red. Probability of an 8.0 earthquake is very high out here. This is the San Jacinto Fault. This is the Elsinore Fault. In our area in Orange County, we have our Newport Inglewood Fault, which has the highest vulnerability for Orange County. And then there's Los Angeles. In fact, they should just put dark red for all of LA County. And they can include Ventura County. Because LA, you have the San Andreas Fault system. You have the Blind Pointed Hills Thrust Fault, and plus numerous other thrust faults that are in the LA basin. And then, of course, you have the Newport Inglewood Fault that goes right through Long Beach. And so Los Angeles, the city of Los Angeles, has vulnerability from the southern segments of this fault, which could generate energy right near Los Angeles. They have vulnerability up north here in the Crystal Plain. A lot of vulnerability for Los Angeles. Orange County, a lot less vulnerability. We do have the Newport Inglewood Fault, and that's the one fault that would worry me of all the faults in Orange County. So as it turns out, the reason the San Andreas Fault does not move uniformly is because there are parts of the San Andreas Fault that are straight. And it's these straight segments that allow for movement. It's where the San Andreas Fault bends, where they have these little S-curve bends. These are areas of the San Andreas Fault that are building tension. Lots of stored energy. And these are segments of the San Andreas Fault that can produce an earthquake of a 7 to an 8.0 real easily. So now, wooden structures are certainly the best. But this wooden house, you say, wow, what happened to the wood construction theory? Again, this house was built on very soft sediment, and the foundation collapsed. So if you lose your foundation, I don't care how well built the house is going to collapse. In this case, it did. This is actually during the Whittier quake. So there are faults out here all over the place in the desert. We've recently witnessed the Ridgecrest earthquakes that occurred last July that sent a shock wave all the way into Southern California. We felt that on July 4th, and we felt a couple of the aftershocks that followed that. The funny thing about that particular quake is that the epicenter was actually closer to the town of Las Vegas. I have a friend who lives there out in Henderson, and I was actually laying on my floor watching TV, and I could feel a little earthquake occur. And then the phone rang. It was my friend Dave Callahan, who lives in Henderson. He goes, "Stop sending that stuff over here." They said they really felt it in Vegas. And I said, well, I felt it a little bit, but he says he really felt it. So because of the proximity of where Las Vegas is, and this is what's vulnerable about places like Nevada, where they don't have really good earthquake legislation, and the building codes that we have in California, is that there are faults out in the desert that could generate a magnitude 8.0. And by the time that shockwave traveled and hit Las Vegas, they could easily experience a 6.0. Do they have the building codes that we have? No, not by any means. And the reason for that is they haven't really experienced a major earthquake. And so we're kind of an reactionary society sometimes. We kind of react after the facts. Interesting thing, this is a good trivia question, by the way. So here's San Diego. Here's Yuma, Arizona, right on the California-Arizona border, right on the Colorado River. This is the San Andreas Fault. This is the San Jacinto Fault, and this would be the Elsinore Fault. Yuma, Arizona lies closer to the San Andreas Fault than San Diego. So what city has the highest vulnerability to an earthquake? By far, Yuma. And again, does Arizona have legislation and building codes in place for making buildings safer? Nowhere near to the standards of California, but yet earthquakes aren't going to recognize a political or boundary. The earthquake's not going to stop at Yuma and says, oh yeah, you guys don't have legislation in place. We can't go there. No, the earthquake's going to travel, and that's the way nature works. So 1971, this is again one of those very landmark earthquakes. So last major earthquake occurred in 1933. That was the Newport Inglewood Fault that moved, and that generated what we call the Long Beach quake. So we put in two pieces of legislation, the Field Act and the Riley Act. And so from 1933 to 1971, there were no major earthquakes. People became complacent. They thought that the legislation that was enacted was adequate. And incidentally, at that time, Los Angeles had one of the largest booms in economic growth and building in its entire history. So between 1933 and 1971, no new earthquake standards were put in place. The prevailing technology of the day was to make the building strong, rigid, lots of concrete, lots of steel. We know today that that's incorrect, that we want buildings to be flexible. In fact, when they built this brand new Mass Science building, there were all sorts of earthquake measures placed in this building. The floors have tension bars that go through them. In the stairwells, there's these great big X's as you walk down the stairs with tension bars on them. Those tension bars are designed to transmit the shock wave through the building. That's what we call a ductile building. So ductile means to transmit something. We use ducts in our heating systems of homes. Air ducts move the warm air or the cool air from the air conditioning or the heater into the rooms of your house. In your automobile, you have a heater core. You turn on the fan takes that heat, runs it through ducts, and comes up the little vents in your dash. That's what ductile is. So ductile means we transmit. So the buildings built prior to the 1971 San Fernando quake were built lots of concrete, lots of steel, rigid. We call those non-ductile buildings. Some of those buildings were built and taunted as earthquake-proof buildings. And we soon discovered there really is no such thing as an earthquake-proof building, because the modern buildings that were built as earthquake-proof failed. One of those, Mission Hills Hospital. There was also a Veterans Hospital built pretty much of the same design. And this was taunted as a state-of-the-art hospital that was going to stand up to any earthquake. And in the early mornings of 1971, the San Fernando Valley was rocked by an earthquake. And here's that hospital. This is a cool picture because when you're in a tall building and you need an elevator, they tell you don't take the elevator during an earthquake or a fire. You're supposed to take the stairs. Well, in this case, if you had done the right thing, you would have died. Here is the end of the hallway. This was the staircase. So the staircase basically collapsed away from the building. So you've been in the staircase, yeah, you'd have died. Plain and simple. So here, this earthquake-proof building, this is the emergency room entrance. It's one of those non-ductile buildings. Here's the emergency room entrance. The funny thing is that this is what's called honeycomb architecture. You see the same design in some of the older buildings here on campus. So the buildings on campus have these pillars, these concrete pillars around campus. Those buildings are all non-ductile, and they are all scheduled to be torn down and replaced with new buildings, because those buildings are extremely vulnerable during an earthquake. So if you're in the general education building, in the auditorium on the first floor, if you look up at the ceiling, it looks just like this. A little honeycomb, the lights are recessed up in there. Yeah, not a good building to be in during an earthquake. So basically what happened with this particular hospital is the pillars on the first floor all failed. The whole building kind of rocked over. This is another one of the staircases that collapsed. And this is during the 1971 Silmar quake. Also, a structure that collapsed during that quake was the San Fernando Valley Reservoir. So people in the lower San Fernando Valley experienced an earthquake and then flash flooding because the reservoir literally emptied out during that seismic event. The good thing about living back in 1971, look at the price of gas, 27.9 cents per gallon. Or you can buy the super high octane gas at 31.9 cents a gallon. Of course, back then cars got like, what, 8 miles to the gallon? Or I like to say 8 gas stations to the mile. Here's a building that collapsed during the 1960 Chilean earthquake in Santiago. Top part, kind of separated here in the middle, kind of 6 bolt away. This part here had some damage. But buildings, they kind of act kind of strangely during earthquakes. Some buildings are very vulnerable to earthquakes and others not so. All right, let's switch gears real quick and let's talk about tsunamis. So people often refer to a tsunami as a tidal wave. There's a distinct difference between tidal waves and tsunamis. Tsunamis are generated because of a seismic event, an earthquake. That earthquake travels through ocean water. And when that seismic event, that wave that travels through water, encounter shallower water near coastal areas such as islands or continents, that shallow water doesn't fit the needs of that seismic wave. That seismic wave is used to travel in deep water. And when you start to narrow the water column, as you get closer to shore, that seismic event is then going to pull water back and then lunge it forward into what we call a tidal wave or tsunami. So tsunamis are seismic waves that are caused by an earthquake. A tidal wave, really waves that occur because of tides or because of the gravitational pull of the moon on our oceans. That's what sets the difference between a high tide and a low tide. And there are some areas that experience tidal waves because they have very narrow inlets to water. But basically, tidal waves have no relationship to earthquakes whatsoever. So any event that an earthquake would occur, say off of the coast of the United States, western United States between Seattle and San Francisco, this particular seismic event occurred in Seattle, it's going to send out a shock wave, and that shock wave is going to travel across the ocean. We have in our ocean, in the Pacific Ocean, buoys. They feel these little seismic events. They send that information to a satellite. That information is then transmitted to Hawaii, and they analyze the data, and from that they can actually generate a seismic warning and give some predictions as far as how high the seismic wave will be, the tsunami. We can, with pinpoint accuracy, predict exactly when a tsunami is going to hit a particular area. It's a really simple equation. Basically, distance versus speed. So the faster the seismic wave travels, the shorter time it's going to take for it to arrive. The slower waves are going to take longer time to arrive. And we can basically pinpoint accurately tell exactly Hawaii or Japan or the Philippines or any coastal area when a tsunami wave will hit. What we can't predict, though, is how big the wave will be. Some seismic events that produce tsunamis will generate waves, maybe in sets of threes, some in fives. Sometimes it's the first wave that's the most dangerous one, the most powerful one, and often it's the third wave. In the case of the Indian Ocean earthquake, the first wave was kind of minor. It was the second wave that came in that was much larger. And so prediction of tsunamis themselves, as far as what wave or how many waves there's going to be, if there's going to be a set of three or just a single wave, it's really a problem. It really gets into very complex string theory math. And really, we don't have the computer technology right now to do it. We just don't have the RAM memory in a computer to do those equations. And it takes many, many sheets of paper or chalkboards to do those equations. So this basically shows an earthquake event. Ocean crusher got displaced. It sent out this shock wave. And if you were out here in the deep ocean in a little rowboat, that seismic event would pass right through underneath your boat and you wouldn't even know it was there. It's when the depth of the water starts to narrow as you approach a coastal area, such as an island or a coastal area along a continent, such as India or North America. As that seismic wave, which is used to travel in deep water, encounters shallower water, it then starts to pull back water. The seismic wave gets ahead of itself. The front of the wave starts to slow down. The back is still moving. This results in this wave building up and over. This is not like a wave that you would surf on. This is a wave that basically is, some of these are 2 miles long. And each one of these acts differently. So it's not surfable because it basically walls and it collapses right onto the shore. So in Huntington Beach and in coastal California, we have an early seismic detection system. We have a siren system that we test the first Friday of the month at noon. The sirens go off. Although I'm sure a lot of you are aware that the sirens went off about 3 o'clock in the morning. And it woke me up. I'm like, uh-oh, I know what that is. I'm thinking about my elevation where my house is and how far I am from. I think I'm okay. As it turns out, it was a false alarm. For some reason, the tsunami warning system went off, and I guess a few people panicked, like, oh my God, the tsunami's coming. I gotta go to Barstow real quick, or something. Get away from the coast. All right, gonna change gears real quick here. And we're gonna talk about another type of geological hazard called volcanoes. So volcanoes, a lot of people live in close proximity to volcanoes because volcanoes, when they erupt, they produce rock, basaltic rock, which is really rich in iron. And that iron, when it weathers out, it forms really good soils. So some of the best soils in the world are found near volcanoes. Because when volcanoes erupt, they produce elements like iron, magnesium, potassium. Those are essential elements for growing crops, especially bananas. So a lot of people live close to volcanoes. So the human environmental dangers include the volcanic ash. These clouds are very high temperature, 600 degrees Celsius. They instantly pulverize anything living. The ash can mix with water, such as in lakes or glaciers, creating lahar flows. These are great big flows. People who live further away from the volcanoes can experience the volcanic ash. This is very silica-rich, quartz-rich material. It can penetrate your lungs, causing people to have a disease called silicosis. And then there's sulfur emissions. So sulfur, when it mixes with water, forms sulfuric acid. You can have actually acid vapors enter your lungs. So volcanoes provide a lot of hazards to humans. And so this is a good example of lahar. This is actually Mount Pinatubo when it erupted. And so this is a lahar. This is the volcanic ash as it mixes with the water, the ice, the glaciers that are in the mountain if they had glaciers. All this material travels down. These lahar deposits travel about 300 miles an hour at the fastest, 150 miles an hour at the slowest. You can't outrun them. And then an interesting thing about this is that the area of Tacoma and Seattle, Washington, these areas are extremely vulnerable to lahar flows. Mount Rainier is going to erupt. When it's going to erupt, we don't know. That's the problem with volcanoes. Volcanoes are a lot like earthquakes. We get a little warning in advance, like when Mount St. Helens erupted. We knew Mount St. Helens wasn't going to erupt. The problem with Mount St. Helens, we didn't know what type of magma was going to come out of it. If it was an iron-rich magma, it would have flowed out lava. It would have made great coverage for the news. But in the case of Mount St. Helens, it erupted very silica, very quartz-rich magma, and that made the volcano very explosive. Mount Rainier generally erupts on the explosive side. So here's Mount Rainier with its glaciers. Mount Rainier has some beautiful glaciers on it. When that hot ash comes out of Mount Rainier, it's going to take these glaciers, it's going to melt it. All that material is going to flow down river valleys, and it's going to inundate these small little red dots, which are bedroom communities. So a lot of people live in or work in Tacoma and Seattle, and they commute, and they live in these little bedroom communities, like McMillan and Ordie and Pacifica. As it turns out, all of these bedroom communities are built right on top of old lahar flows. So they're built on areas that the past eruptions of Mount Rainier has erupted, and it has flowed these lahar flows. So this is kind of what the lahar flow would have looked like if you were around back in the day. This is what they'll look like someday in Seattle and Tacoma. It's going to occur. The problem with volcanoes is they're a lot like earthquakes. We just don't know when. So here is the lahar flow. These are the old lahar flows, and we built these bedroom communities right on top of it. Now, as far as Tacoma and Seattle itself, it's questionable if these lahar flows reached that far to the west or not. But definitely if the wind was blowing in the right direction, it depends on weather, these towns could be inundated with the volcanic ash. And like there's a lot of factors that play into here. But this region is definitely going to see a major eruption from Mount Rainier. Mount St. Helens is considered the sister volcano to Mount Rainier. Those two volcanoes are considered sister volcanoes. And so when Mount St. Helens erupted, it produces this catastrophic eruption, this hot glowing ash. This is the lahar, and these travel very fast. This is actually the result of Mount St. Helens. This was the forest. So this previous picture here shows the trees in the foreground, the ash in the background, and all the green foliage completely stripped out. And this is what's left of the forest. So these lahar flows are very serious. Mount St. Helens, in one eruption, took all this area. So this dotted line shows what Mount St. Helens looked like prior to the May 1980 eruption. This is what Mount St. Helens looks like today. Lots of material ejected in a very short period of time. In the past, we've seen volcanoes impact society. In 79 AD, Pompeii was a town on the flanks of Mount Vesuvius. Pompeii was buried in ash, and so were the people. The modern town of Naples is built right on the ash deposits and the ruins of that old town Pompeii. Today, as they excavate and dig down to put in foundations for tall buildings, they come across the mummified remains of the people who lived in Pompeii and the buildings. And their mummies are basically rock. They basically were engulfed and entombed into hot volcanic rock. So what was the lesson from Pompeii? None. We simply built another city. So all this is another one of those infrared photography slides. So everything that's green turns red. And what I like about the IR band is it really enhances the urban aspects. And so look at, we built our cities all the way around this volcano. Will Mount Vesuvius erupt? Definitely, it'll work again. The last time it did was in 79 AD. It's had some small minor eruptions since then, but nothing catastrophic at all. So Mount Rainier. I was lucky to get this shot of a commercial airliner because generally when you go to Seattle, it's always, Mount Rainier is obscured from the clouds. And so here are the glaciers. This is the west side. They think because of the nature of the rocks on the west side of Mount Rainier that when it erupts, it's going to erupt on this west side. And it's going to blow all its material towards Tacoma and Seattle. And so that hot volcanic ash is going to mix with these glaciers. It's going to melt those glaciers, creating these mudslides, these lahar flows. And these lahar flows are going to float down Mount Rainier. And they're going to basically follow the old path of the old. So these are mountains and these are valleys. So basically this is an area where you have mountains and you have little basins, valleys, another mountain and valley over here. As it turns out, the lahar flows tend to follow along the basins, and coincidentally, this is where we build all our homes and our cities. And so the big next geological disaster to hit the Seattle-Tacoma area will be in this particular area. It'll be a lahar. All right, last topic for this, landslides. California is vulnerable to landslides because our topography is steep. Unlike the eastern seaboard of the United States, where they have a large extended continental shelf, California doesn't have a continental shelf. When you leave our coastline, you go into deep marine waters instantly. So this is a map showing the probability or the vulnerability of some areas to landslides. So if you're in the white areas, you have a low incidence. If you're in these purple areas, you have a very high incidence of landslides. In Orange County, we've had landslides. This is actually in Los Angeles County. Humans kind of add to the landslide dilemma by building buildings. We like to take hills and contour them, make them nice and flat so we can put different pads for homes. These homes are basically heavy structures. Around the home, landscaping, which is mostly irrigated by sprinkler systems, so the water, the weight of the building, and the fact that we built these buildings in very soft sedimentary material, and we completely recontoured these hills. These are kind of things that humans kind of add and we increase the incidence of landslides. This is actually one that occurred in Laguna Beach not too long ago. This followed a fire, so there was a fire, and then the following year, rains occurred, and the lack of vegetation, the general instability of the area, the building. So we come in and do things like we'll remove the toe of the hill, completely cut the toe out, we'll recontour, and then all it takes is a small fire, and then that followed by some rainfall events, and these areas are very vulnerable to landslides. Malibu. We have to build expensive homes right on the coast, and during high tide, the waves are cutting right against this cliff face. This is soft sediment, and so this is wave-cut erosion, and it's a matter of time before the waves cut away enough of this cliff that it's going to fail, resulting in that house to slide into the Pacific Ocean. Point Fermin, California, this is right at the end of the 210 freeway in LA County, so this is near San Pedro. And this is actually an area where they had developed some homes. They brought in a consultant because they realized that these homes were sliding away. And so one of the consultants told them to plant trees. And what type of trees do you think Californians plant? Palm trees. Yeah, we planted palms, which aren't even a tree. They're actually a grass. So this area literally slid away. So here you can see the foundations of some of those old homes. So this entire area slid away. This is a really neat case example. This is actually between Santa Barbara and Ventura. And this is a community that did all the wrong things or the right things to create a landslide. One thing they did is they took the natural hills and they removed the toe. So they removed the bottom of the hill, they took the toe, they truncated it. So what I'm talking about when they're talking about removing a toe, this would be a modern hill, naturally occurring hill. What humans like to do is we like to cut out that toe. And so in that case, they remove this toe. Now, all the vector force is right at this. So we'll do things like reinforce it. So this is called toe removal. And when you do that, you are setting up for landslides. And that's because all that force is now. So we'll do things, put a reinforcement here. We might put in concrete or various structures to help maintain the integrity of that wall. And that's one of the things they did here in this particular community, is they removed the toe all along here in order to accommodate more houses. And the upper part of the hill, they recontoured this entire area here and they put in an orchard. Those orchards then required water, so they added water to the mix. Then there was a fire. And the fire basically removed all the vegetation in this particular area right here. So those factors basically resulted in a huge landslide. So the area in yellow is the area that started to slide first. So that was the first area of slide. This is yellow area right here. And then it was followed by this larger blue area, and eventually it grew over into this region here. So this is the landslide. That's a lot of material coming down. So yes, this house right here on Zillow last week, $1.8 million. Today, $1.80. Very large area came down. They tried to stop the slide by putting in steel and beams, and that was kind of a temporary fix. Eventually, once Mother Nature gets in motion, it's pretty hard to stop. And this is basically what it looks up from looking down at that particular area here. So yeah, we did all the wrong things here. So this is the end of earthquake geology and landslides. And we'll get through the semester, one video presentation at a time. Have a good day.